drawing, so it has to be a good one. So here we're imagining a surface, okay, so between two fluids, say air and water. And this surface, on this surface, we're basically drawing a contour C which loops around some bound surface S. Okay? And we can define three unit vectors on the surface, one of which n is normal to the surface and to the curve C. So we'll call that n. Then we're going to have something which is tangent to both the surface and the curve C. We'll call that m. And then we have S. We have a third unit vector which is normal to C but tangent to S. Call it little s, yeah. Okay? And we know that the interfacial tension is going to act in the S direction, right? Surface tension always acts tangent to the surface, normal to a given curve. Okay, so let's denote the region above the interface by plus, the region below by minus. And so we're imagining there are two different fluids. And what we're interested in is characterizing how the stress jumps as we move across the interface. So both the tangential stress and the normal stress. So again, we denote the interfacial tension by surface tension, by sigma. So let's Okay, so this interfacial tension acts in the S direction. Now we're going to do a force balance on a volume element which encloses S. So let's draw a little Gaussian pillbox. It's artistically ambitious here. See how it goes. But we can ask quite legitimately, when we draw such a Gaussian pillbox, what are the total forces acting on it? Okay? Now let's imagine, so you have to correct this in your notes, that this height here, the height of the pillbox is epsilon, whereas the radius we're going to call big R. And what we're going to do is we're going to take the limit of R becoming much greater than epsilon, so we're going to shrink this down to a tiny surface element, and then we're going to see that that's a vital step. Okay? So force balance. So let's write down the title first of all. So this is stress. Yeah, so you can just touch up your notes, I think, the handout. So again, our goal being the general statement of how the stress changes as you move across the boundary. And this will allow us to then, so if we solve for the fluid in the for the flow in the upper domain and the lower domain, we can see how the two flows have to match together through these interfacial boundary conditions. Okay? Okay, so force balance on our pillbox. You guys use the word pillbox? pill. Yeah, I don't know. They always call us Gaussian pill. Yeah, I don't know. They use it in electromagnetism a lot. Gaussian pillbox.
Why Gaussian?
Gauss did this first. And I saw it first in the context of Gauss's law. Okay, so we can basically say that the total this blob contained within V so that's the net force or the net inertia associated with this blob. So this blob is going to move in response to the external force field applied over V. So this is volume V and surface. And I think we'll just say volume V. We can call it surface of the box. Let's just call it SB. Okay?
So V is the pillbox.
Yeah, V is the whole, is the pillbox, yeah. And we're saying it has surface SB. Okay? Okay, so these are the body forces acting on the fluid elements within V. And then we have the stress Okay, so these are the stress vectors. What we're going to do is we're going to shrink this down. We're going to make epsilon 0. So these then become the stresses acting on the surface. Okay, so these then will become surface integrals over this surface of interest S. So it's basically becomes that in the limit of the epsilon going to 0. Right? Yeah, exactly. So the surface, the top and bottom surfaces of the pillbox are basically going to shrink down. And both become the surface S.
Yeah, but you got a top and a bottom contribution, right?
That's right. Yeah. So this is the top and this is the bottom.
Oh, okay. Yeah. They coincide at the same circle.
Yeah. Yeah. So n hat is simply minus n, right? N hat. Okay. Okay, and so there's another force that we don't have yet. What is it? There's another force acting on this thing. What is it? Surface tension, right? So we have this tensile force acting everywhere around here, right? So there's basically a tensile force per unit length, sigma, acting in the S direction everywhere along the perimeter of the box. Okay, and so now this is a integral around the closed curve C. So this is a line integral. So yeah, officially, but then we would just have one of these terms, right? Right. So I could write that. Yeah, in general that's SB with just T of n, but we have to take the top and the bottom surface, right? So I'm just writing it like this because SB is going to turn into S when we take this limit of the things going to the pillbox shrinking. Okay, okay, so this is basically the inertial force this is your mass times acceleration term. The box, and this is the applied body forces. These are the hydrodynamic stresses coming from the top surface, and these are the hydrodynamic forces coming from the bottom surface. Okay, and this is the line integral of the, so this is the effective surface tension. Okay, so now let's take this limit. So now you have to correct the notes at the top of page 2. So epsilon is the typical height. And r, the radius. Of this element V. So these ones are volume integrals, so these are going to scale like r squared epsilon, right? Whereas the other ones are just going to be acting over the surface, so they're going to go as r squared. So the one term is going to be negligible as we take, these two terms are going to be negligible in the limit of epsilon going to 0. Okay? So these are going to go as epsilon r squared, while the surface forces, so all the others are basically surface forces. We're going to go like r squared. So we have that the surface forces must balance. So these guys are the survivors. Okay, and we know how to express these stress vectors in terms of the stress tensors in the fluid domains. We've just developed this. So we have n dot t whereas t n equals n dot t hat. So that's the stress tensor below the interface. And so up here we have velocity field, pressure field, and stress tensor. And because n hat is just minus n, we have this. Okay, so we see that just from the geometry. Okay, so the last thing we need to do. We have to turn this line integral into a surface integral, okay? Because we want to put these on equal footing, and then we can say that our geometry is arbitrary, so it's got to be a pointwise statement. So in order to do that, we have to turn this into a surface integral, and you can do this using Stokes' theorem. So this is derived in the handout. So it says that this line integral around C of the surface tensile force can be expressed as a surface integral Okay, so there are two components. So let's just define. So this is actually an important step. It's important that you understand it. If you want to be able to derive it, that's your own business, but we need to understand what it actually means. Okay, so it's saying that taking the line integral around here is the same as taking a surface integral of two things. One is this term, so this is the gradient of the surface tension. So if surface tension, I haven't explicitly stated that it's constant, so there could be gradients. So we're driving this in all generality. So this can be non-zero, and this can be non-zero if there are gradients in chemistry or temperature at the interface. And then there's a second term, but this is necessarily tangential, right? So this is going to be, there's got to be tangent to the surface because the gradients of the surface tension have to be tangent because a surface tension is only defined at the interface. Then we have this term which is normal to the interface, and this looks just like our Laplace pressure, right? It's the surface tension times the divergence of the normal. Okay, so let me define what grad sub S is. I just realized that I haven't done that. So grad of S equals so you're basically subtracting off the normal component of the gradient operator. If you want to be formal about things, you can also just think in terms of you're basically just subtracting off the component of the normal, which is, or the component of the gradient, which is normal to the interface. Okay? Sorry, one second. What's that?
There's a triple line under D. Is it 2 or is it different from
this?
No, at the beginning. No, in that line.
Here.
There are 3 lines.
That's an I. That's I. That's the identity matrix. Yeah. So this is the tangential gradient operator, and why do we need a tangential gradient operator? Because surface tension is only defined on the interface, so what does it mean to take its gradient perpendicular to the interface? It doesn't mean anything, right? Similarly, the normal is only defined on the interface, so it's meaningless to talk about the gradient in the normal in a direction normal to the interface. Okay, but really, so. I'm just being formal with this, but we're just going to forget this when we define the Laplace pressure. Previously, we said it's surface tension times a divergence of the normal. Okay.
So basically, the first term, John, can be just due to surfactants effect.
That's right.
There's no surfactant; it's just Laplace.
That's right. That's right. Yep. So you see, immediately there are two jumps in stress across an interface. One is this is the so-called Marangoni stress. Yeah, but apart from that, if you have homogeneous, if there are no gradients in surface tension, all you have is a jump in normal stress which is the Laplace pressure. So it's the surface tension times
It's like in the composition
divergence to the normal.
Marangoni Laplace.
Yeah, that's right. That's right. Yeah, yeah.
Just one more thing. I mean, if you look at n hat is equals to minus n on the
Yeah, because
line here.
yeah.
Yeah, but he shouldn't have lost his hat, right? Because it's not.
Ah, sorry. Yeah, yeah, yeah.
the same, but-
Yeah, good point. Yeah, yeah. Sorry, that was an oversight. Okay, so, and this is again appears because surface tension and the normal are only defined on the surface S. Okay, so we thus have the surface force balance So again, by turning this into a surface integral, we can express this whole statement now So henceforth in the course I'll just drop the subscript S, but it's understood if you see divergence of the normal that I'm actually talking about the surface gradient operator, ditto for gradient of surface tension. Okay, so that's true for any surface S. Right? Since it's true, we haven't specified anything about S. That being the case, it also must be true pointwise, because we can take an infinitesimal S. Okay, so this has to hold pointwise. So we then have our pointwise stress balance equation. Okay, so what do these terms mean? So this is the hydrodynamic stress being applied at the interface by the upper fluid. This is the stress being applied by the lower fluid on the interface. And this has to be balanced, so there's a difference in these two things resulting from these two contributions. So this is, let's call this, so this is the so notice this has a normal component. So this is the normal basically with a magnitude given by the Laplace pressure, and this is a tangential stress which we'll call Marangoni stress. So Marangoni is just a very nice name. I actually was curious why it was called Marangoni, and he was a very obscure scientist, and he published something. I think people liked his name because the first guy to look at a Marangoni flow was Thomson, Lord Kelvin's older brother, did this thing on the wine tears, and it was something like 25 years before Marangoni published his work, but he has some paper on Marangoni stresses on these flows in like the Padua Town Journal. So it's a very obscure thing. Howard Stone managed to track it down, but it's an interesting quirk of fate. I think if you have a really nice name, then you're more likely to have something named after you. There are too many things named after Thompson and his brother, I think, already. So, but in any case, so we have these two components of the stress jump across an interface. Okay, so this is the stress by upper fluid, and this is that associated with the lower fluid. So these in general will have both normal and tangential components, right? And so what we'll do now is write out the normal and tangential components. So we see that this purely has a normal component, this is purely tangential. So both components have to match. So their normal stress balance. So again, if we've solved for the flow above and below, then we know both the velocity field and the pressure field from which we can calculate these components of the stress tensor, right? Okay, so if we take the normal projection of this, so let's call this star. So N so we have N dot T dot N minus N dot T. Okay, so that's the jump in normal stress across an interface is prescribed by the Laplace pressure. Okay, but it does tell us, so in PS, in the situation where if we have a static situation, then we know that the stress tensors depend only on the pressure field. And so it's basically saying that the jump in pressure is given by the Laplace pressure. Okay, and so we'll do a number of examples next class, the static meniscus, where you can simply solve this equation. But one can, in general, have a static situation in which there's curvature, right? So there's a jump in pressure because of the presence of pressure here. Okay? So you can have static situations in which there's a jump in normal stress. But you can't have the same, as we'll see in a moment, with if there's a jump in tangential stress across an interface, it cannot be static. Okay, so tangential stress. So we can pick, of course, there's more than one tangent at a given point on an interface. So we can let's define our tangent as T. So that's but at any given point, there are many tangents to the surface. This is true for any tangent T. Okay. Yep.
When you have a fluid,
Mhm.
and you have different pressure inside and outside,
Mhm.
this normal stress balance is the mean curvature equation?
Is the
Mean curvature. The surface has to have constant mean curvature?
it has to have constant if the pressure jump is the same across it. So typically in a bubble, the internal pressure will equilibrate. If it's a static situation, you have the same pressure inside everywhere. Okay, so that's saying that the pressure jump has to be the same, so the mean curvature will be the same.
So this is like a generalization of constant mean curvature surface.
Idealization of
Like a generalization of constant mean curvature surface.
yes, I would say so. And I mean, again, it depends on the dynamics. So this is simply saying what the local jump in stress is. But you can have situations where, you know, if the dynamics is important, you have dynamic stresses as well as curvature pressures, right? So in general, it's more complicated. Things are simple if you have static situations and there's no gravity. Then you're simply going to compute, calculate surfaces with zero mean curvature, right? And so those are the soap films we saw, for example, at the beginning of the class.
So let me make a comment. If I understood Rocher's comment, if you don't have viscosity, but you have situations where you have a shear flow imposed, for example, it's called the Kelvin-Helmholtz instability.
Yeah.
Then the pressure jump could be different at different points because the curvature could be
So
different.
you will have like a prescribed mean curvature surface.
Yeah, so sort of, not
So
described,
the
it's like the dynamics will determine.
The difference of pressure is like the mean curvature at that point. It's a function.
Yeah,
Different
it will be
pressure
a function.
between
Yeah,
inside
yeah.
and outside.
Yeah, and
He's talking if the pressure is the same, you have a minimal surface. If the pressure is constant but different, you have a constant mean curvature.
Right, that's right. Yeah, yeah. Yeah, and so in general, it's more complicated. So that is the simplest possible thing is the fluid system where you're just minimizing the surface energy, which is basically find the surface of zero mean curvature. Right? But in general, there will be other pressures coming in. If you have gravity, for example, so you have if you have a blob of fluid, and the only thing that matters is this interfacial tension will be spherical. If it's sitting in the presence of a gravitational field, then the hydrostatic pressures are going to increase as you move through the drop, so that's going to change its shape further. And then if there's flow within the drop, it's going to vary not only as the curvature is going to vary not only as a function of z, but as a function of position throughout the drop in response to the dynamic pressures. But this indicates how it happens formally. Okay, so let's just take a look at this. So these are Marangoni stresses. So these are basically the gradients in surface tension. Since in general surface tension is a function of temperature, and chemistry. So for example, as the temperature increases, the surface tension goes down. So also adding soap, so the surface tension decreases with soap concentration. And so, but there's an important point here. Remember that these tangential, this basically pulls out the tangential components of the stress tensor. And remember, the tangential components of the stress tensor don't have pressure in them, right? They only have viscous stresses. Okay? That being the case, this left-hand side only involves velocity gradients. Okay? So if this is non-zero, these velocity gradients, there's nothing to balance these velocity gradients, so you have to drive flow. So you cannot have a static situation in which there's a Marangoni stress. Okay. So that's here. Okay, so this is an important point. If you have a gradient in surface tension, there has to be flow. You cannot have a static situation. It's absolutely impossible to have a static situation in which there are surface tension gradients. And that's different from here. Here we could have a jump in normal stress. So we could have a Laplace pressure which is balanced by internal pressure. So for example, a static bubble. Right here we have P naught, but it's static, right? You absolutely cannot have, so for example, if you have a flow which, so here, if you have a bubble, say, sitting in a fluid, and let's just say it's hot, let's say it's cold here, relative to here, say it's a bubble in your coffee, the surface tension is going to be higher here than here. So there's going to be a gradient in surface tension. That can only be balanced by stresses, by viscous stresses. So it has to drive flow, and you'll get a flow which looks like that. It's impossible to have a static situation, although you see your bubble sitting at the top surface of your coffee, and you won't necessarily see the flow. There has to be flow if you have a gradient in surface tension. Okay?
Does that LHS stands for?
Sorry, left-hand side. Left-hand side, yeah. Okay, so much of the course is really fleshing all of this out, but this is a very important point, is recognizing this. So you can have situations where there's a large pressure jump, a large Laplace pressure, but you can still have, things can still be static. But whenever you have a gradient in surface tension, you're basically, there's going to be some balance where you're saying, gradient of surface tension is going to be mu du some component, dx component. And so you're going to get a characteristic flow, which is prescribed by the Marangoni stress. And it's always, you can never have a static situation. Okay, let's, got a few slides here for you. I'm getting the technology.
Right button, on top, right button.
Yep. Make it flex.
So much of the physics of interfacial flows we've seen today. Are we on here? What's going on here? Will that work? The air conditioner in my office as well?
No, doesn't work. Air conditioner. Oh, I have to compare.
I think it's on.
Press. Yeah, actually.
Open sesame. Very good. So, okay, so we've just developed these interfacial boundary conditions. And again, this is kind of a key step because it's very easy to think about surface tension as being a tensile force per unit length tangent to the surface, right? But the question is, how does it enter into pointwise boundary conditions, right? And we saw that through this. So the net effect of this tensile force acting around this arc length. So basically this line integral gives rise to equivalent to a surface integral. So you get a curvature pressure or Laplace pressure coming in, contributing to the normal stress balance. And then you have the tangential component being the Marangoni stress. So basically surface tension has two net effects. One is to contribute a normal curvature pressure, again proportional to the surface tension times the divergence of the normal. This is going to act, so if you start off with a flat surface, you put some bump on it. Surface tension wants to keep it flat, and it wants to do so to minimize the surface energy in the system. But you can see it's so when you think of water waves, for example, we know that gravity doesn't want to have bumps on the surface, right? Because that's going to increase the gravitational potential energy. Similarly, bumps are going to increase the surface energy owing to the influence of surface tension, so it's going to want to keep it flat too. So you basically have two possible mechanisms which are going to want to keep an interface flat, both gravity and surface tension. And which one wins? Well, we know that's going to depend on scale. So from the scaling arguments we've done last week, we know that if these bumps are small relative to the capillary length, so if they're sort of millimetric in scale, then surface tension is going to kill them faster than gravity. Okay? And so you have two types of waves according to whether the waves are big or small. The waves, there's a balance between fluid inertia and either gravity or surface tension, both of which are the restoring forces. So large waves, the sorts of things you surf on and you see around Copacabana Beach are, of course, gravity waves, and then the small ripples you see in ponds and so forth are typically interfacial capillary waves. Okay? And so the second thing we've seen is that these Marangoni stresses can arise from gradients in surface tension, which come from gradients in temperature and chemistry. And when you're actually solving one of these problems, it can get pretty difficult, because if you have, so for example, if you have a situation where the surface tension is changing considerably as a result of temperature, then you have to, in addition to Navier-Stokes, you have to solve for the temperature within the fluid. So there's some simple situations in which you can do that, but things get ugly quickly, and we'll actually go through some of these. And also when there's surfactant, so when there's a soap, the chemistry can get really nasty. But in principle, this is how you do it. So you have to augment the Navier-Stokes equations with some equation which governs the evolution of the surfactant equation, or of the surfactant, or the alcohol concentration, or the temperature within the fluid. So the things then become coupled through the influence of the second phase on the surface tension. Okay, and so we saw that, but once we've got this, then we basically have the governing equations which we're going to use through the rest of the course. So we have Navier-Stokes equations, and then this just indicates a jump. So this is saying a jump in the normal stress is given by the Laplace pressure, the jump in tangential stress by the Marangoni stress. Okay, but we've basically derived these now so we can get on with our lives. Okay, and so, but again, to stress the two physical effects, surface tension gives. One is this a tendency to keep the interface flat. So it gives, in this case, will give, by deforming the interface, it's giving rise to pressures which can support the weight of this creature. And so this is basically an indication of the normal stresses generated by deforming a free surface. And the second is, again, these Marangoni flows. So we have this jump in tangential stresses prescribed by the Marangoni stress. Can be, so this is temperature, concentration, and that's surfactant concentration. And so this is a soap boat. So you basically, this is a very simple thing to do. You can take a toothpick. Let's just imagine we have a boat here, and we're going to put a chemical on the back. Let's look from above. So we're looking from above, top view. And we know that there's a tensile force per unit length everywhere. Right? We have sigma, 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 sigma. But this is smaller, right? Because the surface, so this is soap. That's right, it's soap, but you decrease it by about a factor of 3. What's that? Oh, that's a sigma. Right? So these are the same. So you basically have the surface tensions everywhere the same, so there's no difference from this side, but the surface tension, so the force per unit length, is higher there than there. So as a result, the thing will move in this direction, right? Okay, and so that's exactly what you see here. And it's very easy experiment to do. You just take a toothpick and you put soap in one end. You put it on the surface of water and it goes shooting at a speed which you can calculate. You basically balance the Marangoni stress integrated over this length, right? Because the total force... I'll put that on a problem set. So, right? So, but you know what the force is, right? Because you're just integrating the force... the Marangoni force sigma S, so that's dl. So you're basically integrating that around, so that's going to be equal to, so this is the contact perimeter here, C. So it's going to be, if this is, if that says W, then it's going to be 2, so it's going to be W times sigma minus sigma, so we call it sigma naught, sigma soap. Okay, so that's the driving force, and then it's going to be balanced by whatever the appropriate hydrodynamic stress is, whether it's going to be viscous stresses acting along the side of the boat or the bottom of the boat, or a dynamic pressure if it's moving at high. So then you equate it to rho u squared. But that basically tells you how fast it goes, and it goes actually pretty quickly. And so here's an application of this, which is being...
There's a trick, right? I tried that once in a bar with friends and it didn't work.
What happened?
I put a toothpick with soap and I tried to show that to friends in the bar. My boat didn't move. So probably
what else was in the drink?
Just water, glass of water, whatever.
Really?
Yeah. If you just use any soap, it works.
Should do, yeah.
You need it to leave a long time in the soap, so it gets really...
Yeah, because one thing is if you put it in, like eventually it'll saturate. Good question, actually. So, speaking of in a bar, so if you...
Bar dynamics, huh?
Yeah. So, but if you so you put in a toothpick with soap on the end, then it'll basically zip around for a while, but then eventually the soap diffuses everywhere, right? And so then it can no longer work because there's no longer a gradient.
Mine didn't move. I just put a little bit of liquid soap. It didn't move. The liquid soap was a bad soap.
It might, well, you also, if you contaminate the surface, if for example, if you're drinking from your glass with lipstick,
I was.
lipstick, lipstick, or if you put your finger in it, then the body oil will act as a surfactant. So if you contaminate the surface ahead of time, it works much better with clean water, right? Because clean water has the highest surface tension. So probably what happened is you or someone you were with drank from your glass and was wearing lipstick and contaminated. But it's interesting. And I've showed you earlier in the class. There's a bug that uses this, right? So there's a bug that releases a chemical and uses exactly this mechanism for propelling itself across the surface. So but it can only. This only goes for a limited time in a closed domain such as that, because eventually the whole surface becomes contaminated in a surfactant, and so the surface tension equilibrates across the body. So the only way, and this is one of the few instances where I've not found a biological creature that uses the mechanism, but if you use a volatile surfactant, okay, you can actually get the thing to go forever. So basically, if it's releasing if we imagine that our surfactant now it hits the surface, so decreases the surface tension, and then evaporates, then the thing can keep going and going and going. Okay, that's right. Because you never saturate the surface, and so that's what we did here. So alcohol does evaporate, and so this is our soap boat, our cocktail boat. So it's in a martini glass, and we basically have pure alcohol in there, and it basically just keeps going until, of course, runs out of fuel. And they're using that in a bar now, in this very high-end bar in Washington. Jose Andres has been developing this. But it's basically it's actually quite striking, because the thing moves around at a pretty decent pace, right? So, what's that? Well, it's the shape of the fuel release, right? So my student was Lisa. What is it?
It's not. The fuel is not coming out on a constant.
Yeah, it's kind of coming out at an angle. Yeah, just to make things interesting. Yeah. But so again, I've not seen anything in nature, but presumably it must be very energetically costly for creatures to metabolize to create a volatile surfactant. That's the only reason I can imagine why they don't use it. Scale, yeah. But it's a martini glass, this one. So. Yeah, the soap will definitely stay on the surface, and this stuff basically hits the surface and then evaporates. But I have some other.
Next time I do my toothpaste experiment, I'm going to do it with my father-in-law. He always drinks a martini on Saturday. So.
Yeah, that'll work. That'll work better. No, but again, having the larger the difference, the better, right? So this is I think this is just water with alcohol, just get the maximum bang for the buck. Okay, that's good. We'll see you on Wednesday if there are no further questions. Any questions?